Hi, welcome to this video lecture. My name is Professor Cody Powell. I'm continuing my Smart Systems course. In this particular video, I'm going to talk you through how to develop a dynamic model with coupled differential equations. So in past videos, we had this very simple tank model where we had our tank with volume V. We had our flow in was Q in, our flow out was Q out. That led us to the development of a really simple model that's a volume balance, which gave us dV dt is equal to Q in minus Q out. This followed this material balance formula where we have the accumulation in our system equals what comes in minus what leaves. But we could also have another term that is either a generation term or a consumption term. In this particular case, if we have a constant density fluid, then the volume is going to be conserved. What if our system was not just a tank, but rather a chemical reactor? So let's assume that what's flowing in is component A with a concentration of C sub A. Inside the reactor, we have this reaction where A converts to B, and these are sort of fictitious chemical compounds. So leaving the reactor, we would have some kind of concentration of B, but because the reaction may not go to completion, we also might have a concentration of A. We're going to use the assumptions of a CSTR, and this is an impeller here, which spins and keeps everything well mixed. So the assumption with a CSTR is that the concentrations are uniform throughout the volume of the reactor. So I'm going to walk you through how to develop the equations for this type of model, where we're going to result in having not just one differential equation like you see with the volume balance. We're going to have the volume balance plus two more differential equations representing material balances on components A and B. I'm just going to quickly show you some of the specs of the variables that we will be considering. So we'll have flow in, flow out, the volume, the height of the reactor, the concentration of A, which will be expressed in kilomoles per meter cubed, the concentration of B, which will also have that same rate. But then we also need to know what is the inlet concentration of our reactant, which we're going to express as Ca naught. That's going to have a nominal value of 15 kilomoles per cubic meter. We're also going to need to use some of the same model parameters from our gravity drain tank model, but we will introduce a new parameter, this K naught, which is the reaction rate constant for this first order reaction. So as we develop the model, this is where we're pulling this data from. All right, so just like we had our volume balance, we will do material balances on components A and components B. So again, we'll start off with this accumulation term, in, out, and then let's call this consumption because we're going to start with component A. So this is a material balance on component A. So we're going to think about our system, again, with that same kind of a control volume. However, now we're going to be thinking about how much A is in our reactor. So because we're given the concentration of A, with the CSTR, we're assuming that this component A is uniformly mixed throughout. So we can write the total moles of A in the system is just going to be our volume multiplied by the concentration of A in our system. So our accumulation term is going to be the rate of change of moles of A. So we're going to have a derivative, d by dt, and what goes inside this derivative operator is going to be the total number of moles of A in our system. All right, similarly, what's coming into our system, remember we had our Q in and our Ca not coming in. So if we multiply that volumetric flow rate by that inlet concentration, that's going to give us the total number of moles coming into our system. And if you did a unit check on each of these terms so far, you should get that each of these are expressed in terms of kilomoles per minute. All right, so what is leaving our system is going to be Q out. I'll draw a straight line there. So we have Q out, and because the CSTR is well mixed, what leaves the system is the same as the concentration that's mixed throughout the system. So what's leaving our system is going to be Q out multiplied by CA. And I made a mistake here. We're calling this flow rate Q in. All right, so notice we have two different flow rates and we also have two different concentrations here. So A is also going to be consumed in our system as this reaction from A to B happens. And the reaction rate is going to be given by our first order rate law. So I'm going to create this new variable called R reaction, which is going to be equal to our K, and remember that was K0, multiplied by the concentration of A multiplied by the volume. So again, if we did a unit check here, we should get that this has units of kilomoles per cubic meter. So I'm going to go ahead and put that into our consumed part of the equation. All right, so we've defined accumulation, in, out, and consumption. So now what we would do is we would do what I call compile this energy balance. So we would just say accumulation equals in minus out plus consumption. And I will just add in these operators here. So we put an equal sign, we have in minus out, and it's being consumed, so we have a minus sign there. All right, so now this is a differential equation, so we could plug this into Simulink and solve it, just like we did with our volume balance. However, knowing this quantity, we would know the total number of moles of A, or the rate of change of the total number of moles of A, but what we actually want to know is this term dCA dt. We want to solve explicitly for dCA dt. So I would modify this equation using the product rule. So the product rule would tell us that if we did V times dCA dt plus CA times dV dt, this whole term is equivalent to the derivative of V times CA. So it's we just break it up using the product rule from calculus. So now we're left with this quantity on the left-hand side. So this still equals everything that's on the right-hand side. So what I would do is I would take the right-hand side and I take the left-hand side rather and solve that explicitly for dCA dt. So I'm going to skip some steps algebraically here, but you can go through this a little more slowly on your own if you would like. So we get dCA dt is equal to everything on the right-hand side. So we have Q in times our CA naught minus Q out times our concentration in the reactor minus K naught times CA times V. Then we would need to subtract this term, this CA dV dt term, and then we need to divide that whole left-hand side by V, or rather multiply it by 1 over V. So here we have solved explicitly for dCA dt. The way we're going to do this in code later on is to realize that our code already solves for dV dt with our prior differential equation. So we'll have dV dt available in the code, and then we can incorporate dV dt when we're solving for dCA dt, which is the rate of change of concentration of species A with respect to time. So let's do this a little bit more quickly for component B. So component B, we have the same reactor, we still have the volume, we have Q in, we have Q out. We're going to have some kind of concentration of B in the reactor. So if we look at our accumulation of B, that's still going to be the same. d by dt of our concentration of B multiplied by our volume. Let's think about the other terms, in, out. And in this case, B is a product, so we have A goes to B. So B is actually generated in this reactor. So we're going to use a generation term here. All right, so because B is a product and there's no B in our incoming fluid, this in term is actually 0. Our out term is Q out multiplied by the concentration of B. And then our generation term is just the opposite of our generation term, or of our consumption term for A. It is K naught times CA times our volume. So the generation of B still depends on the concentration of A. So if we break that out like we did before, we would say accumulation equals in minus out plus generation. We would break this out using the product rule. So specifically, that would give us V times the change in the concentration of B with time plus CB times the change in volume with time equals minus Q out times CB plus K naught times CA times V, which would be the amount generated from the reaction. So we would do the same exact thing. We would solve for dCB dt, and that is going to equal everything that's already on the left-hand side, so minus Q out times CB plus our reaction rate. Now we're going to subtract off this term, minus CB dV dt, and then we would divide that whole thing by V or multiply by 1 over V. Just to summarize really quickly, we now have our 3 differential equations. So the first of those is here, dV dt equals Q in minus Q out. We then have our dCA equals everything here on the right-hand side. And then finally, we have our dCB dt here. So this is what we'll use in our simulation in the next video.